Welcome everybody to this week of the Big Data for Engineers lecture. Today, what's on the menu? We will finish looking at performance at large scales. I still have to show you some kind of relativistic effects that we have at large scales. That is something that you wouldn't expect. But if you ever work in a large corporation and have a lot of machines, then this is something that you will definitely observe. So I'll show you that. And then we'll start with document stores. That is a technology that was invented 2 decades ago, 1 or 2 decades ago, to solve the problem of when the data is not normalized. Because we saw with Spark SQL, I showed you a bit the limits of Spark SQL, that when the data starts having nested structures and when it has type mismatches and so on, it's a bit messy. Then SQL has its limits, right? And so in the remainder of the lecture, we are going to explore how these limits were actually solved with technologies, right? Before we start, however, I will start as usual with a few clicker questions for you, and then we'll take it from there. So let me switch over to the other screen. Okay, so here's the first question for you. So you remember the tasks and the slots. It's actually both for MapReduce and Spark, right? It doesn't really matter if it's MapReduce and Spark, but we saw what a task is and we saw what a slot is. What is the issue if every slot would just process one task? We saw that in practice, a slot can process several tasks, right? But what if we create as many slots as there are tasks? Which could be as many slots as the HDFS blocks, for example, because there is typically one task for each block. So what is the issue? Is it that some tasks may take longer and most slots will be idle waiting for the last ones to complete? Are there no issues at all? Maybe there are no issues at all. Or is it that all slots are busy and not available for starting with the next phase, and that leads to non-optimal performance? The last answer, if a task fails, the whole Spark job fails, the task should be assigned to 2 or 3 slots for fault tolerance. So let's see what you think. Okay, let's take a look at incoming answers. I see there are less answers than the people actually present, so do not hesitate. You can just go to the website eduapp-app1.ethz.ch and just log in with your ETH credentials. It's that easy. Of course, you can still install the app of your phone on your phone if you prefer, but it's really as easy as opening your browser to get there. All right, we have a majority. And the majority says that some tasks are going to take longer because the duration is not the same. And that means that once the shorter tasks are over, all of these slots will be idle waiting for the tasks that takes the longer. And in fact, you are correct. This is the correct answer. This is exactly what happens. All the slots start at the same time, and then everybody is basically waiting for the slot that takes the longest for the task. All slots are busy? No, on the contrary, they become idle. Once a slot is done with their unique task, they are idle, right? So in fact, this is the reason why we assign several tasks to each slot. And the fourth answer is made up. There is no redundancy for the task assignment, even though we'll see that it may make sense in this lecture. All right, no, not yet. That would be a bit early. Here's another one for you. What does the second version of MapReduce? We saw that there was the first version, and then there was a new design of the architecture. So let's call it MapReduce 2. What do MapReduce 2 and Spark have in common? The first is everything. They are exactly the one and same technology. Spark is just the name that was given to MapReduce 2. Or they have a processing model that is based on fully generic directed acyclic graphs, both of them. Or Both of them are based on Yarn for resource management. Yarn is for yet another resource negotiator. And the fourth answer is their input and output models. Their input and output model is more flexible. Records do not need to be key value pairs. All right, only 12 answers, 14? All right. Do not hesitate to participate, right? It makes it more interactive. It's more fun if you actually participate in these questions. Okay, oh, we have two competing answers. The correct answer is that both of them are based on Yarn. This is the correct answer. MapReduce 2 is exactly the same model as MapReduce 1. That didn't change. It's still collections of key value pairs. It's still map followed by reduce. It's exactly the same. It's just that behind, we use Yarn for the management of the resources of the memory and CPU, but that's it. So the second answer is incorrect because it's only Spark that has a processing model based on these DAGs, directly acyclic graphs. MapReduce 2 is still based on a simple map shuffle reduce model. All right, from the perspective of the user, there is no difference between MapReduce 1 and 2, by the way. It's really something that's completely hidden behind that the users won't see. Do we have a question on the chat?
So Spark cannot be used without Yarn?
Yes and no. There are actually competitors to Yarn. Yarn is not the only resource manager that there is out there. There's others. And you can also use Spark with a different resource management system if you prefer, right? But you need one. You need a way for Spark to basically obtain the resources on the cluster. It doesn't have to be Yarn, but Yarn is kind of let's say the first one or the default one. If you don't know what to choose, then just pick Yarn, right? All right, thank you for the question. Okay, do I have other questions? Yes, I have plenty of questions. Oh, this one, that's the last one. We are going to look at document stores later today. So here's an appetizer for that. Documents, what is a document? It's actually an XML or JSON, an XML element or an XML document or a JSON object. And basically a document store, as we will see, is just a collection of JSON objects or a collection of XML documents, right? So my question here, what do you think? Of course, I didn't tell you yet, right? Because we are going to do that later today, but try to guess. How does a document store like MongoDB store documents physically? Does it store them as text files, directly like JSON text files on top of HDFS? MongoDB queries are automatically converted to MapReduce or Spark query to process these text files, as we saw in the lecture. Or as an optimized binary format called BSON on the local hard drive, and JSON types, arrays, and objects are efficiently stored and basic atomic tags are supported. Or third answer, as text files, JSON on the local disk, and they are parsed on the fly with a very efficient technique called just-in-time parsing, right? That's inspired by Java, just-in-time compiler. Okay, and the fourth one, crowdsourcing. There is a document center done under the Antarctic where little elves store and retrieve documents on paper. They nicely sort them on shelves organized in racks. All right, what do we have here? Oh, nobody likes my little elves. Okay. So it is the second answer. The majority is correct. The second answer is correct. It's actually an optimized binary format. Actually, it should make sense to you because do you remember what I told you? That if you have a JSON data set it's more efficient to convert it to Parquet, which is a binary format, and to read from Parquet. Does anybody can remind me why using a binary format like Parquet, or in that case Bison, is more efficient than text? Can anybody give me a reason in the lecture hall or on Zoom? Any idea? Why is that? Or you didn't have your morning coffee yet? Anybody? Why is Parquet, a binary format, why is it more efficient and faster than having a full-fledged JSON file?
Maybe because it's smaller?
Yeah, exactly. That's the primary reason. It is smaller. And the reason why it's actually better that it's smaller is that very often the bottleneck, so the issue why your overall data query is slow when you try to query your data, is going to be because you cannot read fast enough from the disk. So as you can imagine, if the file is smaller, then you will read it from the disk faster because there's less to read. There are less bits, there are less zeros and ones to read. So this is the reason why the size actually is important. And this is the reason why it's really a big deal if you can compress and make the data smaller, right? So this is very important to understand. And there is another answer.
Right, it's a similar comment saying that the keys do not need to be repeated.
Absolutely. In fact, this is the reason why Parquet is smaller. The reason why Parquet is smaller is that it doesn't repeat the keys, right? In JSON, you repeat the keys. Of course, you use a lot of redundant bits to repeat the keys. So I repeat, keys do not need to be repeated in Parquet. And as a consequence, the Parquet file is smaller. And as a consequence, it takes less time to read it from disk. And because the limiting factor is reading from disk, the whole data querying is going to be faster. And the idea behind Bison in MongoDB is the same. It's binary, it's smaller, and thus it can be read faster from the disk. All right, since we are talking about performance, let's just continue about performance, right? So I will throw a few high-level tricks at you. It's a bit computer sciencey, right? So I teach that to the computer science students. I know you're not computer science students, but nevertheless, I think it can still be useful if I explain a bit to you. But of course, don't worry that much, right? Just try to get the essence of what I'm going to tell you, the sort of things that we do to optimize things. So the idea is that whenever you have a query on and you're querying a data set, imagine you're not just going to, unless you are incredibly gifted, you are not going to manage to write the query correctly the first time, right? You would need a lot of luck to just get the query right and then run it, and then you have the results, and then that's it, right? That's not how it works. You probably saw it. You need to repeat and repeat and repeat and fix your query and change and adapt and run again and run again and run again. So it's basically running it plenty of times, right? And because of that, the faster each execution can be, the faster you will be done writing your query. There is nothing more frustrating than having to wait for 10 minutes every time, and then you notice it didn't work and you change it, and then you need again to wait for 10 minutes. So if you can reduce that to just 30 seconds, it's more pleasant. In fact, that was exactly the experience of the people who preceded us at ETH or other universities. Back then, we didn't have computers as we know them today. We have the luxury of having our computers and our screen and typing things, and we can query the web and instantly know everything. Back then, we didn't even have screens. What we had were these punch cards with little holes in there where the computer programs were punched with the little holes. And what happens is that the researchers, so the PhD students or the students who needed to execute programs for their research, they prepared in the office the punch cards, and then they had to bring it to some room at ETH or wherever it is at a university that runs these programs. So they basically bring their punch card, they put it on the stack, and then they come back the next day. And in the meantime, the people responsible for the execution are going to take care of it. Guess what? It's batch processing. They basically just take batches of these programs for many different people, and then they just run the batches like that. And then people come back on the next day, and then they see the results of the program. As you can imagine, very often they came back to realize that the program didn't work. And back then they needed to wait every time one day, like 24 hours, every time they had to fix something. It was very frustrating. So you can see how today we are in a much better position for that. And we even complain about 10 minutes or 1 minute, right? But anyway, if you can shorten that, that's better. So how do we talk about these things from a performance perspective? What we look at very pragmatically as a data scientist, what you are interested in is the time that elapses between the moment you press enter in your Jupyter notebook and the moments that the results are printed on your screen or available on disk. This here is the total response time, right? It's basically the latency, so the time it takes to set up everything or, you know, for things to trigger, so that's the waiting time, plus the transfer, because the data needs to flow around in the cluster and be transferred over the network. So all of that together, the latency plus what we call the throughput also, is the total response time. So if you manage to improve the system to make it faster by one way or the other, then you get a speed up. And how do you compute the speed up? Very easy. You just measure the time that it used to take and the time that it takes now, and you just divide. For example, if you have 3 seconds to run something before the improvement, and then you improve it and it only takes 2 seconds, what is the speed up? It's 1/2, right? Just divide.
Yes. Yes.
Yeah, perfect. You got it on Zoom. All right. So you see, you just divide. Before divided by, it's like in these fancy ads, right? Where they put pictures of people before and after. So you basically just divide before by after, right? All right, so that gives us a speed up of 1.5 because we managed to get it down from 3 to 2. All right. Now, in reality, what happens is that you have a system like the implementation of your like Spark or MapReduce or whatever. It's a computer program, and that computer program has many parts. There's the part that's reading from disk. There's the part in memory. We saw like the disk, the memory, the disk out, the network, and so on. All of these parts together execute the query. When you improve something, usually you improve it specifically for either the disk or the memory or the network. You know, you basically improve it somewhere, but not everywhere. That means that you can actually get a speed up only on part of the system. A concrete example of that is when you parallelize data. So for example, imagine that 30% of what's going on in the cluster is parallelizable. And imagine you manage to get a speed up of 2, but not on everything, just on the parallelizable part. Maybe, for example, because you just doubled the number of machines and then that's it, right? So that shortens. Then the formula to compute the speed up is this 1 divided by 1 minus p plus p over s. It's actually because of this old divided by new, basically. The old was 1, and the new one is you basically fix the parallel part. So the part that was inefficient, that's p, that's the percentage, 30%, goes away, and you replace it with the faster part, right? So for example, you used to have like 0.3, and now you have 0.15 because you managed to double it, right? So if you do this division, as an example, you get a speed up here of 1 divided by 1 minus this 30% that were inefficient, replaced by having the time that it takes. So if the speed up is 2 just under a parallel part, the overall speed up on everything, including the non-parallel part, becomes 1.80. So this is a mistake that many people make. They believe that, you know, as soon as you optimize the parallel part, everything just goes away, but no, you actually lose efficiency because you only optimize part of the system and not all of it, right? That is actually the motivation for always trying to focus your effort on the part of your system that is the bottleneck. Otherwise, it has no effect. You will barely observe anything. Imagine that you take a part of the system that is just taking 1% of your time, and you manage to triple the efficiency of that 1%. Who cares? It was only 1% of the system. It doesn't change anything that you manage to optimize 1% of the system. But if you manage to optimize like 30% or 50% of your system, then you have a visible impact in the output, right? So the lesson here is focus on the bottleneck. Try to find out where the bottleneck is. Is it the disk that can't be read fast enough, the memory, and so on and so on. But somebody else had another idea. So Amdahl came up with that law. Somebody else called Mr. Gustafsson came up with this different law. They said, no, that's not 1 divided by this thing. It's 1 minus p plus sp. They basically compute it differently and say, okay, 1.3 would be the speed up here. So of course, we have a problem here because two people compute different things, depending on how you reason about the speed up of your system. So of course, who is right? Turns out the answer is very simple to explain. And that's also something you see in real life. For example, Amdahl's law says your problem size is finished. You have a specific data set, you have a specific query, and you manage to just shorten the time that it takes to compute your one query. Then this is this formula that applies. In reality, though, there is something that actually happens very, very often. Is that if something is a bit inefficient, and then you improve it and make it better, what's going to happen is that you get even more people that are going to start using it. Right? So this is one of the side effects of improving things, right? You say, okay, let's do it more efficient. And that's actually something that is also discussed in the context of global warming, right? Because in some cases, what can happen is that you improve the efficiency of something that in order to diminish, for example, the carbon emissions. And what actually could happen is a phenomenon that since it reduces the carbon emissions, let's use it more. But actually, overall, you actually make things work. So this is the Gustafsson's law that basically says you keep, in that case, for data, you keep the computing power constant, and you just use the available computing power that you get with your improvements to solve even more problems. Right? So you have these two approaches. All right. So let's get to the tuning. I'm done with this complicated formula for the speed up. Let me talk to you about something concrete. It's the tuning of Spark when you execute Spark. Right? So we saw that we can scale out by adding plenty of machines. Turns out we can control how we scale out. We can tell the system. We can also scale up. You can control the amount of memory and the CPU on the machines. Right? Scaling up, of course, I told you, I warned you, it's the last resort. You should first try to scale out and then scale up. Right? So what do you scale up when you need to scale up? When you can scale up more CPU power, more network bandwidth, more memory, or a better disk, maybe a flash drive or SSD and so on. All right. So how do we avoid these things? Well, here I'm going to stay on the surface. I'm not going to go too much in the details, but this is what computer scientists do. In order to avoid memory scale up, they try to avoid wasting memory because you can actually waste memory. You can use a lot of memory in a very efficient manner. So in that case, what you look for is every object in your programming language that is here billions of times. For example, if you have a collection of billions of JSON objects, you look at how to store these objects. Because imagine that you manage to more efficiently store one of your JSON objects, all of that is multiplied by billions. So if you had, let's say, a side that it takes like 10 gigabytes in your memory, this whole collection of billions of objects, and you manage to reduce it by a factor of 2, you go from 10 gigabytes to 5 gigabytes. If you have 8 gigabytes of memory, that makes a big difference, right? Because suddenly you are within your bounds, the bounds of your memory. So this is what computer scientists do. They look for all the parts that are repeated billions of times. Everything you have something that is stored billions of times, this is where you need to focus the effort in order to store it more efficiently. Next, how do we avoid CPU scale up? Here also, there can be huge wastes of power. And that happens typically in the repeated loops. When you have for loops, you know the for loops, right, from programming. Well, when you have a for loop that repeats billions of times, and that happens in big data, what is a for loop that repeats billions of times? When it's the call of the map function, for example, or the call of the reduce function, this is a function that gets called billions of times, right? So this is the place to look at. You need to implement your map function or your reduce function or the functions in Spark as efficiently as possible, because this is what gets repeated in gigantic loop. This is where you need to focus. So I added here a few, don't worry too much about the details, but these are all the things that computer scientists need to be careful about, right? Too many method calls, too many overridden methods that costs resources, very deep class hierarchies. Of course, you're taught that in object-oriented programming, the class hierarchies are great. But if you abuse hierarchies, then it becomes very, very slow. Instance of is also consuming in resources, casting is consuming, throwing exceptions, and so on. So these are all the things that we try to avoid, especially on what repeats billions of times. Then we have the disk-IO scale-up. So here we've already talked about that. Compression. Use Parquet instead of JSON. Use BSON for MongoDB instead of text JSON. This is how you actually scale. So in efficient format, you avoid repeating the keys and potentially you compress. There's even compression techniques. All right, so this makes a difference if you store it in raw syntax or in a binary format, and binary formats are more efficient. All right, how do we avoid the network scale up, right? The fourth one. Here, the keyword is push down, push down, push down, push down. Whenever you shuffle, you remember this thing. So in the middle of MapReduce, there is this shuffling where you shuffle the key value pairs. And in Spark, there's also shuffling whenever you have a transformation that is a wide dependency, right? For example, the distinct transformation is a wide dependency, the join, the group, and so on. Everything that shuffles things around causes a shuffle in the network. Here, we need to do something called push down. We actually already saw that. I just didn't tell you it was called push down. When we did the combine in MapReduce, this is in fact a push down. What is a push down? It's to try to reduce the amount of data that gets shuffled by computing or aggregating this data before the shuffling. That's exactly what the combine function does, because you already call the same as the reduce function on each map slot before it gets shuffled around. For example, if you're computing sums, if you pre-compute partial sums and only ship the partial sums, you reduce the amount of data that flows over the network. So you see, between the memory waste, the CPU waste, the disk IO waste, and the network IO waste, there is a huge amount of possibilities that make your resource consumption more efficient. And also, as a consequence, your queries much faster, right? So these are all these techniques. So I gave you, again, on a high level, these are typically things that it's the computer scientists usually that deal with that a bit more, but it gives you an idea, right? We look for what's repeated, and we just optimize. So we want to keep this shuffling to an absolute minimum. The thing about shuffling is that everybody hates it, but we can't do without it, because if we couldn't shuffle, then we couldn't join, we couldn't group, we couldn't reduce and so on. But we still want to keep it to a minimum. All right. So here's an example on how now you allocate your machines with Spark. You could have a cluster of 8 nodes with 16 cores on each node and 128 gigabytes of memory per node. These are your machines. These are basically the machines I'm giving you in a cluster that you reserve on Azure, on Amazon AWS, and so on, right? So 8 machines, 16 cores on each, and 128 gigabytes of memory on each. So now the question comes, how do you create your slots or your executors in Spark? One way of doing that could be this. You say, okay, let me have one executor on each machine. So I have 8 executors, and each executor has 15 cores. It means that it's capable of executing 15 tasks in parallel, right? And with the shared memory for all these 15 cores, they share the memory of the executor, which is 100 gigabytes. Right? So now maybe you're wondering, okay, why not 16 and why not 128, right? But it's because you cannot use everything. You still need to keep a few resources for the overall administration of the cluster, right? So this is the reason why you need to be slightly less. But then this is basically how it goes. All right. So 15 cores, 100 gigabytes, and so on. And this is the pictures I showed you in the past few weeks, that then we have 15 tasks in parallel on each executor, And in total, it's 15 times 8. It's 120 tasks that are thus executed in parallel on that cluster. All right, this is approach one. Approach two is to say 1 core per executor. So I have these 15 cores, but I'm going to create 1 executor for each one of them. So now I have 15 executors on each machine. So I have 120 executors. I still have a parallel capacity of 120 tasks that I can do in parallel. The difference is that now we are no longer sharing memory. There is 8 GB for each executor, and they are isolated, compartmented, right? So then you can no longer, if you have a task that needs more memory or less memory, then that can cause issues, right? So this is one extreme. This is the other extreme of the way that you allocate your core, and you have full control over that, of course. And in practice, what people do is somewhere in the middle. They basically use like 3 times 5, for example, right? I usually go with trying with the square root or something, right? Around the square root, like have the same number of cores per executor and executor per machine. So you can say, okay, 3 executors of 5 cores each. So now you have 5 tasks here in parallel on each, right? So it's still 120 tasks in total. But now the memory is shared 5 cores by 5 cores, right? 30 gigabytes. Usually this is the sweet spot. This is what you want to have roughly. Of course, you need to compute that again every time you create a new cluster and you have different machines, but this is the idea. And that's how it works. I give you the parameters, right? For Spark Submit, you can control all of these three aspects. Of course, if you use the Jupyter notebooks, you don't really see it, right? Because this is happening in the background with PySpark, right? But if you really get serious with production-ready queries, then you will configure these things. All right. By the way, some of you saw in the TA sessions, there is this localhost 4040 website that gets created when you execute a Spark query. There is a lot of interesting things that you see in there, a lot of pictures and visuals about the internals. And this is also where you see this. You actually see the slots and the tasks.
What's the issue with sharing our 100 gigabytes between the cores? And what are the disadvantages of the 2 others?
So here, let me start this one because this is the more obvious. Here, the disadvantage is that the tasks might not all be the same. There might be tasks that take more and tasks that take less memory, right? So here you might be stuck because a task will need a lot of memory while other slots will not use the entire memory. So it's inefficient. Here, I think that it causes too much, this is something I understand less, it causes too much pressure over the access to the network by the same process, because it's the same process. I can try to look for that again, the exact reason, right? It's not on the top of my head, but this is also not optimal, basically. You really need the sweet spot. Right? Can we take a note when and try to again, look up a more precise reason why this is inefficient?
Sure.
Okay. Now, ideally, that's the question I asked. This is what you would expect with 1 task per chunk. Wrong. This is what happens in reality. The tasks will be short, and one of the tasks is going to take more time. This is the reason why you want more tasks than slots. Right? Chunks or tasks is the same, right? Task blocks, chunks, it's all the same. So you want to be able to have a bit to spread all over, right? So this is more efficient. So for example, if you have 10 times more tasks than slots, then you're good. Like 10 slots and 100 tasks is a sweet spot, right? Because then you can fit more on those that are faster and fit less on those that are slower. Do not push it, because if you say, okay, let's have then 1,000,000 times more tasks than slots, then okay, no, that doesn't work, because remember that every time you have latency, every time you start a task, you have some latency. So if you have 2 small tasks, you will just be in latency all the time, and you can come back in 1 year for your results. So you need to have a sweet spot in the middle, like some factor between the two, but not too high. Right. So this is because, again, the network bandwidth is limited, and yeah, you need to be careful, right? So let's say 5 times, 10 times is a good factor, right? Okay. And of course, if people are not happy, they can build a new Spark. In fact, it's more for computer scientists, but people still try to invent new technologies and solve new problems, right? But right now, Spark is actually quite popular. All right, now let's talk about the relativistic effects that happen on my cluster. In an ideal case, what will happen is that the nodes will all finish at the same time, right? Because we spread these tasks over the nodes, right? So ideally now all of your slots, those that are faster will have more tasks, those that are slower or less tasks, but they more or less finish at the same time. Usually it's not exactly that, it's more like this, right? So if you have a cluster with 5 machines, then this is what you will observe. There is a bit of idle time at the end, but this is okay, that's fine. Now, if you are at very large scales, thousands of machines, 10,000 machines, you would expect to see something like this, right? Like with 1,000 or 10,000. This is what you would expect, right? This is reality. In reality, what happens is that 1,000 machines are going to compute things, 999 will do just fine, stopping after some time, and then one machine is going to go crazy and just take an enormous amount of time. And it has to do, I'm not going into the details, but it has to do with background stuff that's happening on the machine. You have plenty of resources that are managed by the machine. And what happens is that, for example, you know about the garbage collection in Java. The garbage collection is something that can happen anytime in the background, and then you're unlucky and it just starts, right? So there's plenty of complicated and technical reasons in computer science that basically make it so that if you have an enormous number of slots, you're almost doomed for one of these slots to just encounter an issue like that and take forever. This is called the tail latency, right? You will have, for example, typically you express it like in 99% of the cases, it's going to take less than 1 second, right? The typical one being 10 milliseconds, 99% of the cases, less than 1 second. But in that 1% of the cases, it's just going to take forever, right? So then you can do some probability theory. If it happens that you have a chance 1 in 100 to take forever, what is the chance that you are lucky and that all of the machines that you put in the cloud, none of it had this problem, right? So this is basically, if you did a bit of probability theory, it's basically a union thing, right? It's either you say, okay, from the perspective of no problem, it's an AND. It's a multiplication of independent probabilities, right? So no problem here, no problem here, no problem here, no problem here. Multiply the probabilities. Or if you do it the other way around, like there was a problem here, or there was a problem here, or there was a problem here, you need to do this mathematical gymnastic with 1 minus p to the power of n, right? if you repeat. But in any case, I'm sparing you the probabilities. What happens is that on a single node, of course, in 99% of the cases, it's less than a second, and in 1%, it's more than a second. If you have 10 nodes, then you will see that in roughly 90% of the cases, it's still taking less than 1 second, but it will happen in 10% of the cases that you take more than 1 second on at least one machine, right? This is already a bit bad, right? You might be lucky, but it might be bad. But look, 100 nodes now with a larger query. Now I'm only lucky in 37% of the cases, meaning that I have 2 chances in 3 that this is going to happen, and then one of the slots just takes forever. 2 out of 3. This is really impractical. If you have 1,000 nodes, then you would be extremely lucky if you don't have the issue. So you see, you're almost guaranteed that with so many nodes, this is going to happen, right? So you could think, okay, let me just improve that number. Let me just build a system for which it's in 99.99% of the cases that I have this 1 second guarantee. So you would think, okay, that fixes the problem, but not at all. Because again, already with 2,000 servers, you are back to having the problem in 20% of the cases, right? So basically, there is a very interesting article that I am putting the link if you're interested, that even if you are very conservative, if you scale up the number of servers, you see the issue is not negligible, right? So all kinds of improvements that computer scientists can think of, nothing works. Nothing of that works. And this is very surprising to young graduates that join a company and think they can just write better code. No. They always have these problems that one of the machines is just going to take enormously longer, right? So this is really, really, really bad. Fortunately, there are ways that we can fix these things. Fortunately, there are a few tricks that people actually use. One of them is the fact that you duplicate all your tasks. Imagine you have 100 tasks, just execute each task twice, right? You just give it to 2 slots, every task. what's going to happen is that one of the slots might go crazy like this, but you don't care because it was executed somewhere else as well. So you can just wait until at least one slot completed each task, and then you don't care if the other one gets into that problem, right? So it consumes twice as many resources, but the problem goes away. Right? So again, you duplicate the execution of all of your tasks. Another one is called deferred head request. It's another trick. In that trick, what you do is that you take some time to do some experimental analysis with your cluster and try to compute the entire, the percentile table of your latency, right? So you say, okay, in 50% of the cases, it's less than that. In 90% of the cases, it's less than that. In 95% of the cases, it's less than that, and so on and so on. And of course, if you increase the percentile, then it goes up. And then you say, okay, I just execute my MapReduce or Spark job. I don't duplicate the task, right? I just execute one task just once on one slot, each task. And then I just let it run. And then I will observe one of the nodes that goes crazy like this. And I wait until the amount of time that elapses is in the 95th percentile, meaning that it takes more time than 95% of the time. For example, what happens then is that you say, okay, that's it. I've had enough of it. Let me just take that one task and give it to somebody else. Right? So now I just let it be with this one, and I just contact another node, another slot, and say, okay, can you re-execute that same task right here? And then, of course, the probability is very small that you are out of luck here because it just once. Right? So you just launch the duplicate task when you do that. And then you cancel the one that took longer. So you see there are tricks to do these things. And here it's just experiments that I think they did at Google in order to test this thing right there. And then they noticed that they went from, I think this was the 99.9% percentile of the overall job, of the execution of the job, that it used to take 1 second at that percentile. And they reduced it with this technique here to just 74 milliseconds with only 2% more requests. These 2% are these extra ones that you launch right there. So basically it works. So this is it. I hope I didn't scare you because yes, I know that was a bit technical. It's actually typically something that is, we go more in depth for computer scientists, but nevertheless, I hope it gives you a bit of an insight and an idea about the world of, the computer science side of big data, what we call data engineering, basically. So do we have a question?
Yes, one question is that, but there will still be one machine that is the worst performing. What should be the acceptable difference between the worst and the best, or between the worst and the worst of the best?
I see. So what you really need to picture is that it's not just a tiny difference between the machines. It's like on 1,000 machines, 999 will be just fine. And then suddenly in the last percentile or the last part of the percentile, it just goes like unmanageable, right? So it's really not so much a thing of, the best or the worst. It's really a thing of once in a while with a probability P, your machine just goes nuts, right? I'm not sure if this answers your question.
Yeah. Another question is that we could also directly give the task to an idle node and stop at the fastest answer.
Yes, the problem is that you don't know in advance. Because when you gave the task to this machine right there, it was idle when you gave it the task. And it's after you gave the task that suddenly something happens and it takes forever, right? So this is the problem. You cannot know until it happens. Right? And what you do here is that you do look for an idle node. They are all idle actually when that happens, right? And then you give it there. I'm not sure if that makes sense. Exactly, all the other nodes are idle. There is just one that is just annoying everybody else, right? So we can give them, yes, absolutely. This is what happens. This is exactly what the deferred hedge request is. When you see that this is happening, that one node takes forever, this is exactly what you do. You pick one of the other idle nodes and you give the task, and then you forget about this one. That's exactly it. You got it. Oh, without waiting, well, you can set it to whatever you want. Right here, I put 95. You could put it to 50%. I mean, this is really up to you. But the thing is, what's going to happen is that you might duplicate too much, because the lower the percentile, the more often you will have to do that, right? So it's a compromise between, you know, how much you're waiting and how many resources additionally you want to consume. So there is really a value here that is a parameter and that you can set freely. Yeah, does it make sense?
Can I just speak? Yes.
Yes. Okay. Go ahead. Speak.
But the idles node are idle completely, or we can still use them if they are idle? Because, for example, it doesn't make any difference if we multiply the task many times, because like in this picture, I don't know, like 19 of the nodes are completely idle and one is really rushing and having a hard time. So maybe we could just duplicate the task 19 times and we just keep the fastest answer. And
the reason why you don't have to duplicate 90 times is that what happens when you are here, what happens is that all tasks are done except just one. There is only one task that is remaining, because all the other ones, they got spread to the others. So you have one task that you need to execute. If you just do it once, just once, the odds that you will have the problem on these other nodes are extremely low. This is the reason why you don't need to duplicate it 90 times, because this is really something like once in 1,000 times. So it's just one task that you redo, and you can really almost assume that this is going to succeed, right? And in the worst case, you do this one more time, but the odds that it fails twice are so small that you can just consider it negligible.
Yes, but my point was that, for example, I don't know, the 95 percentile is like 2 seconds. And there is a node that is idle after 0.1 second. So if we know that this task is taking really long, we can directly give it to the node that finished really, really quickly, like in 0.1 second. And maybe this node will be able to finish in also 0.1 second, and we can finish much faster than waiting for the timeout of the 95 percentile.
Yeah, I got you now. Yeah, I think it's very smart. Indeed, this is very smart. So it's basically a third way out. I don't know if they thought of it. It might be that some people did. Basically, so one technique is to duplicate everything from the beginning. Another one is to wait for the percentile. What you're suggesting is that as soon as node starts being idle, we instantly start duplicating the tasks, no matter what the percentile is. That's your suggestion. Yeah, exactly. Very smart. I like that. This is actually very smart, and I think it could work.
Okay, cool.
Yeah,
thanks.
Very nice. Thank you for this. All right, let's take a break. I'll see you as always at 10 past 11 for the continuation of the lecture. See you in a while.